And what if I told you there's something in the universe capable of erasing everything that exists? Not just destroying it, but literally deleting reality as if it had never been. You probably think of black holes as cosmic monsters that devour stars, gravitational giants where nothing escapes, not even light. That image is in every documentary, in every spectacular NASA illustration. And it's incomplete in a way almost nobody notices. Because the real problem with black holes isn't what they swallow. It's what they do with information. Information sounds too abstract to matter, right? But here's the crucial point that's about to flip everything upside down. In the physical universe, information isn't just data on a computer. It's the essence of everything. The exact position of every particle. The spin of every electron, the velocity of every photon. Everything that defines the state of the universe at any moment is information. And according to the fundamental laws of physics, the same ones that make your phone work and keep the sun burning, information can never be destroyed. Never. Under no circumstances whatsoever. When you burn a book, the information in it doesn't disappear. It spreads into the ash, into the smoke, into the heat released. In theory, if you were smart enough and had absurdly precise instruments, you could reverse the entire process. You could reconstruct every letter, every word, every period. Because the laws of physics are reversible. What happened can, in principle, be undone. Always. This isn't philosophy. It's quantum mechanics, it's thermodynamics, it's the basic structure of known reality. So imagine this. You throw that book into a black hole. Now what? Seems simple. The book crosses the event horizon, that invisible boundary from which nothing returns, and vanishes forever. End of story. But wait. If information can never be destroyed, and the black hole swallowed the book completely, where is the information now? It went inside the black hole, obviously, right? But here's where the real problem begins. A problem so deep that Richard Feynman, one of the most brilliant physicists of the 20th century, became obsessed with it. And he was right to be. Let's go slow. You look at a black hole from outside. All you can measure are three things: mass, electric charge, and rotation. That's it. Doesn't matter if you threw in a star, a planet, or 10 trillion different books. If the total mass is the same, the resulting black holes will be indistinguishable. Completely identical. You can't tell what fell inside. The information about the contents has vanished. But that violates information conservation. Now you're starting to feel the discomfort. Because one of two things must be wrong. Either information can be destroyed and everything we know about quantum physics collapses, or something very strange happens with black holes that we don't yet understand. For decades, physicists tried to solve this and failed. Repeatedly. Then Stephen Hawking enters in 1974 with a bombshell. He proves mathematically that black holes aren't completely black. They emit radiation. An extremely weak thermal radiation, but real. And by emitting this radiation, they lose mass. Eventually, after an unimaginable amount of time, a black hole evaporates completely, disappears, and here's the final blow. Hawking radiation is perfectly thermal, random. It carries no information about what fell into the black hole. So what happened to the book, to the star, to everything that was swallowed? It was deleted, erased from existence, as if it had never been. This isn't just scary, it's a theoretical catastrophe. Because if information can be destroyed, then quantum mechanics, the most successful theory in the history of science, is fundamentally wrong. And if it's wrong, the entire universe stops making sense in the way we thought it did. Feynman saw this abyss opening. He didn't have a solution, but he knew something was profoundly broken. And the most disturbing part? This isn't some minor technical problem. It's an existential threat to the coherence of reality, because if black holes can delete information, then the universe isn't deterministic. The past doesn't determine the future. Cause and effect disintegrate, and everything you think you know about how things work needs to be thrown away. Can you feel the vertigo now? Because we're about to go deeper.
Let's talk about what happens at the edge of a black hole. Not the Hollywood version, the real physics. And it's stranger than anything you've imagined. Picture yourself falling toward a black hole. From your perspective, everything seems almost normal at first. You're accelerating, sure, but space looks regular. Time flows normally for you.
You cross the event horizon, and nothing dramatic happens. No wall, no barrier, no sensation of passing through anything. You just keep falling. But now imagine your friend watching from a safe distance. They see something completely different. As you approach the event horizon, they watch you slow down. Your movements become sluggish. Time itself, for you, appears to dilate infinitely from their perspective. You get redder and dimmer as the light from your body gets stretched to longer wavelengths. And here's the kicker. They never actually see you cross the horizon. Ever. You appear frozen at the edge, gradually fading from view over billions of years, asymptotically approaching the horizon but never quite reaching it. So which version is real? Do you cross or don't you? Both. And this is where your intuition starts screaming. Two observers, both correct, seeing completely incompatible realities. This isn't a measurement error. This is the structure of space-time itself, behaving in ways that violate every assumption you have about how reality works. Now connect this back to information. When you fall in, from your perspective, you take all your information with you past the horizon. It's inside now, gone from the outside universe. But from your friend's perspective, you never crossed. The information never left the outside. It's still there, encoded somehow in the increasingly red-shifted light hovering at the horizon. Wait, the same information can't be in two places at once. That violates everything. Quantum mechanics explicitly forbids identical copies of quantum information. It's called the no-cloning theorem. You can't duplicate a quantum state. Period. Yet here we are, with the information apparently both inside and outside simultaneously, depending on who's asking. This isn't just a paradox. It's a knife cutting straight through the fabric of modern physics, splitting quantum mechanics and general relativity into incompatible halves. Feynman recognized this tension. He knew that when two of your best theories contradict each other this fundamentally, at least one of them is incomplete. Maybe both. But it gets worse. Much worse. In the 1990s, physicists started taking seriously a radical idea. What if the information never actually goes inside? What if everything that falls into a black hole gets somehow encoded on the event horizon itself, smeared across that two-dimensional surface like a hologram? The three-dimensional object you threw in gets translated into a two-dimensional pattern of information on the horizon. And when the black hole evaporates via Hawking radiation, that information slowly leaks back out, encoded in the radiation in ways so scrambled and complex that it looks random, but technically isn't. This is called the holographic principle. And if it's true, it means something absolutely mind-bending about reality itself. Think about it carefully. If all the information about three-dimensional objects can be fully encoded on a two-dimensional surface, then maybe our entire three-dimensional universe is itself a holographic projection from information encoded on a distant two-dimensional boundary. Everything you see, touch, experience, a shadow of something fundamentally lower dimensional. You, your memories, your thoughts, the planet, the stars, all of it might be elaborate patterns dancing on a cosmic screen you can't perceive. Does that sound like science fiction? It shouldn't. This idea has become mainstream in theoretical physics. Some of the brightest minds alive work on this seriously. It solves the information paradox, but the cost is that reality as you perceive it isn't fundamental. It's emergent, derived, a consequence of deeper, stranger rules, And here's what keeps physicists awake at night. If black holes can bring us this close to deleting information, close enough that we need to completely reimagine what space and dimension mean, what happens if they actually succeed? What if Hawking was right, and information really does get destroyed? Then the universe isn't just stranger than we imagine. It's unstable. The rules can break. And if they break once, why not everywhere? See, the laws of physics aren't just descriptions of what happens. They're guarantees. Conservation of energy guarantees you can't create a perpetual motion machine. Conservation of momentum guarantees rockets work in space. Conservation of information guarantees the universe has a consistent history, that the present is fully determined by the past, and the future unfolds from the present according to rules. Break information conservation, and you break causality itself. Effects could happen without causes. Events could occur that have no history. The past could literally change, not our memory of it, the actual past. An object could pop into existence with a fake history that never happened. You could make a measurement that has no prior cause, no quantum state that produced it, nothing. That's not physics anymore. That's chaos masquerading as reality. A universe where anything can happen isn't a universe at all. It's a fever dream, a glitch, a cosmic error message. Feynman saw this. He didn't have the holographic principle or modern string theory, but he understood something crucial. When your theories predict their own breakdown, when they lead you to logical contradictions you can't resolve, the universe is trying to tell you something. It's showing you the edge of your map. And black holes? They're the dragons. So let's push even further into the abyss. Because there's something about black holes that almost nobody talks about, and it might be the most terrifying part of all. Black holes aren't rare cosmic curiosities. They're everywhere. At the center of nearly every galaxy, including ours, sits a supermassive black hole, millions or billions of times heavier than the Sun. Smaller ones are scattered throughout galaxies by the millions. Right now, there are probably dozens within a few thousand light-years of Earth. And they're all doing the same thing, testing the fundamental laws of physics at their absolute breaking point. Every single one is a potential deletion engine. Now here's what should make you uncomfortable. The information paradox isn't solved. Not really. The holographic principle is elegant, mathematically beautiful, and it might even be right. But nobody has actually proven that information escapes from a black hole in Hawking radiation. The calculations are impossibly difficult. The radiation is so faint, so scrambled, so quantum mechanically entangled with the black hole's interior that we can't track where the information goes. We have proposals, frameworks, mathematical arguments, but no definitive answer, which means we don't actually know if the universe is safe. Think about what happens if information really is destroyed, not in one black hole, in all of them, across the entire universe, constantly, over billions of years. Countless objects, particles, quantum states, all falling into black holes and being erased. The informational content of the universe slowly degrading, the cosmic ledger becoming incomplete. What does a universe with missing information even look like? Here's one possibility, and it's deeply weird. If information is destroyed, then the quantum state of the universe becomes fundamentally uncertain. Not in the normal quantum mechanical way where things are probabilistic but calculable, but in a way where the math itself breaks down. You'd have multiple possible pasts that could have led to the present moment, with no way to determine which one was real. History becomes ambiguous. Reality loses coherence. Or maybe the information paradox is a sign that black holes shouldn't exist at all. Not shouldn't in a moral sense, but shouldn't in the sense that a consistent universe following quantum mechanical laws cannot support objects like this. Maybe general relativity, our best theory of gravity, is wrong in exactly the way that allows black holes to form. If that's true, then what we call black holes might be something else entirely. Quantum gravity might step in at the last moment before the singularity forms and prevent true event horizons from existing. The object might look like a black hole from outside, but the interior could be radically different. A fuzzy quantum structure, a firewall of high-energy particles, a wormhole to another region of space-time. Anything but the clean, simple black hole that general relativity predicts. Except we have no theory of quantum gravity. String theory tries. Loop quantum gravity tries. Other approaches try. None of them are complete. None make testable predictions we can verify. We are fumbling in the dark, trying to understand an object that possibly can't exist, according to rules we haven't discovered yet. Feynman would have loved this mess. He always said that the most interesting moments in science aren't when someone says, "Eureka," but when someone says, "That's weird." And black holes are the weirdest thing we've found. They sit at the intersection of quantum mechanics and general relativity like a glitch in reality, showing us exactly where our understanding fails. Now we arrive at the moment of revelation. The moment where everything clicks into place, and you realize the information paradox was never really about black holes at all. It was about us, about what we can know, about the limits written into the fabric of reality itself. Here's what Feynman understood that most people miss. Physics isn't about discovering what the universe really is. It's about finding the best possible description we can construct, given the information available to us. And black holes reveal something profound about information itself. It has a maximum density, a limit, a boundary beyond which you cannot compress more information into less space. This limit is called the Bekenstein bound, discovered in the 1970s. It states that the maximum amount of information that can be contained in a region of space is proportional to the surface area of that region, not its volume. Think about that. Information isn't evenly distributed through three-dimensional space like water in a container. It's fundamentally tied to surfaces, to boundaries, to two-dimensional areas. A black hole is what happens when you try to violate this limit. When you compress so much information into such a small space that the surface area required to encode it collapses inward, forming an event horizon. The black hole's entropy, its information content, is proportional to the area of its event horizon, not the volume inside, the surface. This is the holographic principle crystallized into mathematics, and it tells you something shocking. Three-dimensional space isn't fundamental. It can't be. If information lives on surfaces, then our perception of living in 3 dimensions is somehow derivative, emergent, a projection from something more basic. But there's a deeper layer still. Why does information have a maximum density at all? In classical physics, you could theoretically compress infinite information into a point. Quantum mechanics already limits this somewhat through the uncertainty principle. But the Bekenstein bound is stricter, more fundamental. It suggests that information itself is quantized, comes in discrete units that cannot be subdivided below a certain scale, the Planck scale. The smallest possible length, about 10⁻35 meters. Below that, the concepts of distance and space themselves break down. And here's the devastating conclusion. If space is quantized, if it comes in discrete chunks, then space-time isn't continuous. It's pixelated. Reality has a resolution limit, like a computer screen made of indivisible pixels. Black holes pushed us to this conclusion by breaking our theories. They showed us that when you try to cram too much information into too small a space, the universe says no by forming an event horizon and hiding the interior from view. The singularity at the center, that point of infinite density predicted by general relativity, probably doesn't exist. It's a mathematical artifact showing where the theory fails. Quantum gravity, whatever it turns out to be, almost certainly replaces that singularity with something finite, something quantized. And this is where we find the answer to our original question. Could black holes delete the universe? No, because they're not deletion engines. They're compression algorithms. They're the universe's way of handling information overload. When too much stuff gets concentrated in one place, space-time itself reorganizes to prevent the catastrophic breakdown of physical law. The event horizon forms as a protective barrier, isolating the extreme conditions inside from the rest of the universe. Information gets encoded on the horizon, compressed to maximum density, and eventually released back through Hawking radiation over timescales so long they make the current age of the universe look like a blink. The universe doesn't delete information because it can't. The rules won't allow it. And black holes are the proof. They're the universe enforcing its own consistency, showing us the absolute limits of compression, density, and information storage. They're not bugs in reality. They're features, necessary consequences of a universe where information is conserved and quantum mechanics is real. Feynman was right to be obsessed. Because black holes revealed something that changes everything. The universe is computational. Not in a metaphorical sense, literally. It processes information according to rules, has a maximum information density, operates at a fundamental resolution limit. Reality is a quantum computer running calculations at the Planck scale, and we are patterns within those calculations. Black holes are what happen when you max out the processor, when a region of space-time tries to encode more information than the hardware can handle. The system doesn't crash. It isolates the problem, creates a boundary, manages the overflow. Elegant, robust. Exactly what you'd expect from a universe that's been running for 8 billion years, without a fatal error. But here's the final twist. The one that should give you chills. If the universe is computational, if information is fundamental, if reality is made of quantum bits processed according to laws, then who wrote the code? What compiler turned those laws into the running simulation we call existence? You can't answer that. Nobody can. It might not even be a meaningful question. But black holes, these objects we once thought might delete the universe, have instead revealed that the universe is far more carefully constructed than we imagined. The laws don't just describe what happens. They protect themselves. They guarantee their own consistency. Information conservation isn't just a law. It's the law, the foundation everything else rests on. When you look at a black hole now, you're not looking at destruction. You're looking at the universe's immune system in action. You're seeing the mechanism that prevents reality from tearing itself apart. You're witnessing the guardrails built into existence itself. And that's beautiful. Terrifying, yes. Humbling, absolutely. But beautiful. Because it means the universe isn't random chaos. It's structured, consistent, knowable, at least in principle. We can ask questions and get answers. We can probe the edges of reality and find not madness, but deeper order. Strange order. Order that violates our intuitions and forces us to rebuild our understanding from the ground up. Black holes could have been the end of physics, the place where all our theories failed and left us with nothing. Instead, they became the beginning of something new. A doorway to quantum gravity, to holography, to the computational nature of existence. They showed us that when you push physics to its absolute limits, you don't find chaos. You find deeper law. That's what Feynman knew. That's what he was right about. The universe doesn't break its own rules. Not ever. Not even at the edge of a black hole, where space-time screams and reality bends to its breaking point. Especially not there.